So let's look at some issues for further study. So support vector machines are great if we have a problem that's linearly separable after we've embedded in a sufficiently high dimensional space. But how high is high? And we're going to actually see there are problems that are not separable no matter how high a dimensional space you put them into. So given a separable problem, we can separate it, finding the margin and the support vectors. And what we're doing is we're getting a separating hyperplane, and the margin has a width of 2 over the norm of W, where W is the parameter vector determined by the training data. And we're finding the smallest such W, which gives us the largest margin. And then we predict the class of an unlabeled X by simply taking W dot X and seeing if it's 1 or negative 1. Or greater than or equal to 1, less than or equal to negative 1. But you get the idea. Now, linearly separable is necessary unless we go into a higher dimensional embedding space, in which case we may have a separable problem that's linearly separable in an extremely large dimensional space. Now, in that extremely large dimensional space, let me just mention that we can define terms like above and below and between and convexity, and we can talk about dividing two convex sets using a hyperplane. So everything we've talked about in 2 dimensions still applies in this extremely high dimensional context. But remember that the choice of a kernel is extremely important. So the polynomial kernels correspond to a finite dimensional embedding. The radial basis vector corresponds to an infinite dimensional embedding. You can think of the exponential here as sort of a successor or a polynomial algorithm or polynomial kernel with p going to infinity in some sense. And then the perceptron gives us a neural network-like kernel. So these are the 3 kernels that are used in practice. And of course, the huge question is, how do I know which one to use? Again, cross-validation is going to be extremely important for selecting these parameters, like the P and the sigma and the A and the B. But selecting the right kernel is actually a very important issue. So ideally, you would know the embedding map phi, and if you know the embedding map phi, then you can choose which kernel is most appropriate. But that's not always possible. As a matter of fact, rarely do we sit and think exactly how is something being embedded in an extremely high dimensional space. So instead what we do is we look at how we can divide support vectors into classes. So in 2 dimensions, if we have 3 non-collinear support vectors, we can always divide those into 2 classes with a straight line. And you see those examples here. But now if we had 4 support vectors, then it may not be possible to separate them with a line in 2 dimensions. As you can see here, there's no line that I can draw such that all the zeros are on one side and all the ones are on the other. So we can use a 2-dimensional space if we have 3 support vectors, but not if we have 4. But if we have 4, then we can use a 3-dimensional setting. So what does that mean? That means if we have a 4-dimensional setting, then 3 dimensions means that essentially we're looking at a polynomial kernel with 1 extra term. So a polynomial kernel with p equals 2 is all you need if you have 4 support vectors. But if r is equal to 5, then 3D is too small, and polynomial with degree 2 is too small. If r is 6, then 4D is too small, but 5 dimensions is not. Okay. Similarly, 4 dimensions is not too small when r equals 5. So you see a pattern here. And the pattern is that essentially, if you have r support vectors, the embedding space must have dimension of at least r minus 1. So if A is some subset in Rn, then what you do is you look at what's called a convex hull, which is the set of all convex combinations. And this allows you to always work with a convex set. And then you look at what are called Radon's theorem. We've kind of been looking at a simple example of Radon's theorem. So if S is in R sub D has at least D plus 2 points, then we can separate them with convex sets. And while we don't show it here, it's sort of intuitive that if you have separated convex sets, then you can draw a line between them, which separates one from the other. Or in high dimensions, a hyperplane. So every vector in the training data, if you're starting a problem, you don't know how many support vectors there are. So therefore, every vector in the training data is potentially a support vector. So the size of the embedding space should at least be the size of the training data. However, you're going to be cross-validating, so that means you're going to be getting training, validation, and test sets. Now, how many ways are there to choose the training, validation, and test sets? And it's pretty easy to see. I'm not going to prove it, but there's really exponentially many possible training sets. So when you first go into a problem, if you don't know how many support vectors there are, then there's possibly some exponential of the size of the training data you want to use, different ways of getting support vectors. So that means the dimension of the embedding space should probably be exponentially larger than the size of the training data. Again, these have to be huge spaces. So if you use a large degree polynomial, however, that can oscillate wildly between maxima and minima. So what we have here is a heuristic. You really don't want to use polynomial kernels if you expect more than just a few support vectors. So Radon's theorem implies that any finite dimensional training data, however, is linearly separable in a sufficiently large space. Now, the radial basis kernel is the workhorse. So why? Because you're in an infinite dimensional space. So in general, I would suggest always starting with a radial basis kernel, because there you don't have to worry about if your polynomial is too small or something like that. There's plenty of room in infinite dimensions to put everything you need to put in. So I would only go to a polynomial kernel if you have a small, well-behaved, practically linearly separable problem. So notice that I said finite size training sets have to be linearly separable in an infinite dimensional embedding space. Great. So that means because we only have finitely many data points in our training data, why don't we just always use infinite dimensional? And why did we learn any other algorithms? Why not just do support vector machines with radial basis kernels, and that will be the entire field of big data? Well, there are problems with support vector machines. First off, the choice of a kernel is itself a pre-processing step. And when you pre-process your data, you can destroy information. You certainly introduce bias. That's why we don't ever want to do pre-processing unless we're also cross-validating and making sure that we're getting good results. Because pre-processing can really change the nature of the data if it's done incorrectly and if it's not verified. There's also problems with the concept of separable. So the real world and the data it produces tends to be complex, multi-scale, emergent phenomena. Complex tends to not be separable. Now, a finite set of data may only be one of infinitely many possible that a process can produce. So the assumption of separable implies the existence of a margin, and that points within the margin are negligible, and that no matter what training data you choose, you're essentially going to get the same thing. So let's look at an example that's non-separable. So suppose we have a polynomial z to the fourth minus 1. It has two real roots, plus or minus 1, and two imaginary roots, plus or minus I. We can find those roots at an arbitrary point z0 using Newton's method. So Newton's method, z sub n plus 1 is z sub n minus the function over its derivative at z sub n, which for us is this simple rational iteration. So when we do Newton's method, there's only 5 possibilities. It can converge to one of the 4 roots, or it may diverge. And this is going to be determined by whatever our choice of z0 is. So we're using complex numbers here. So when I think of z0, I want to think of things like 1 plus 2i, things like that. So let's look at a non-separable example based on Newton's method. So we're going to define class 1 as those points z0 that converge to a real root, and class 0 is going to contain the z0s that converge to an imaginary root. And so in blue here is the class 0, is a subset of class 0. Green is exactly class 1. Now, no finite training set is going to imply the kind of separation that we are looking at with Newton's method. There's similar detail at every smaller scale. So if we take a slice here, what we see is there's this infinite dimensional detail at every scale. You're seeing more detail. Notice also that there are points that don't iterate, and those are in black. And so we're also going to say that the points that are black are also in class 0. So we'll explore this further, but let's take a look at the notebook where we actually do this. So first off, I'm going to take a simpler example. So we're going to look at binary expansions in which the frequency of the digit 1 is greater than a half. That's going to be class 1 and otherwise class 0. So we get this kind of an image. So let's use a support vector machine to classify this. Notice we're using radial basis kernel because that's the default. We get an area under the curve of 0.72. So we might be tempted to think, that's not too bad. But in reality, when we look at the decision boundary, so our original data is highly detailed. So it's essentially a Cantor set in any slice. And yet our support vector machine classification is practically just draw the line from 1, 0 to 0, 1. So now let's look at Newton's method with that pretext. So we're going to load the Newton's method data. It's a very large data set. Notice about 250,000 points. So that's not as large as we do in applications, but it's pretty large. But we need that in order to recover the kind of detail that you would need to actually look at Newton's method as a classifier problem. So now let's look at our validation scheme. So we split the data up into training, testing, and validation. Or here just training and testing. And we naively apply a support vector machine. We get an area under the curve of 80%. So again, you might think, wow, that's fantastic. We're just brilliant. Support vector machine does everything. But now let's look at the decision boundary. So the original is extremely detailed. So at every different scale, and yet even though it's a nonlinear classification, it's a very simplistic decision boundary that you see for the support vector machine. The map on the right is a heat map for Atlanta, Georgia. So essentially, across this 23-mile section containing downtown Atlanta, we get this unnatural heating up because of all the asphalt and buildings and activity. And we can think of this as a classifier problem. So we can have class 1, which is orange, which I'm calling hot Atlanta, and class 0 is in black, and that's where you have normal temperatures for the landscape in the region. So if you wanted to predict where in Atlanta you get sort of abnormal temperature, class 1, hot Atlanta, you can see this is a problem that has very many levels of scale, a huge amount of detail involved. So to naively just predict, say with a support vector machine or logistic regression or a decision tree, they just won't be able to produce this, because even if you embed in an extremely high dimensional space, this isn't going to be separable in any sense. Finally, let me say that all of this we've been talking about extends to multiple classes. So if classes are subsets of mutual disjoint convex sets, then linear separability applies. And when we use sklearn, for instance, you can actually use multiple classes. We always use class 1 and class 0, but you can have as many classes as you want. All these ideas extend. So let me just finish up by showing you how logistic regression, and therefore by extension support vector machines, handle multiple classes. So if you've got capital K classes, then that means you have a more sophisticated set of parameters. And your probability models now are exponentials over sums of all the exponentials, where you have an exponential for each possible classification. So each class has its own probability model. You need a threshold for each probability model, P sub k, where k is equal to 1 to capital K. But in each one of those, you would predict x to be in class k when the P sub k was greater than the T sub k, where T sub k is the threshold. So in some sense, everything is exactly as we saw before. Now there is a technicality, and that is that we have one too many vector parameters. So we're going to let the W sub 0 vector be equal to 0. Now let's see what this looks like if m is equal to 2. If m is equal to 2, then our probability model P sub 1 of x is e to the w1 dot x over e to the w0 dot x plus e to the w1 dot x, the latter all in the denominator, that sum. And if I multiply on the top and the bottom by e to the negative w1 dot x, then I get 1 over 1 plus e to the w0 minus w1 dot x. Now w0 dot w1, w1 is a parameter vector, so w0 minus w1 is also a parameter vector. But it's only 1, so we have too many w sub k's in this scheme. But what we do there is just we let one of the parameter vectors be zeros. And if we do that, then our probability model is 1 over 1 plus e to the negative w1 dot x. Exactly what we saw with logistic regression. Looks familiar, huh? And if P1 of x is greater than T1, x is predicted as class 1. What about class 0? It's got a probability model also. So notice that P1 of x less than capital T of 1 is the same as 1 minus P1 of x greater than 1 minus T sub 1. So 1 minus P1 of x is 1 minus 1 over 1 plus e to the negative w1 dot x. And when we do the algebra here, then we get e to the negative w1 dot x over 1 plus e to the negative w1 dot x. And now we simplify by multiplying by e to the w1.x on the top and the bottom. And now we get 1 over 1 plus e to the w1 times x, okay, instead of negative w1.x. Now notice that 1 over 1 plus e to the w1.x is exactly the same as e to the w0.x over e to the w0.x plus e to w1.x. Why? Because w sub 0 is identically 0. And so 1 minus p1, for the case of two classes, 1 minus p1 is equal to p0. Well, what's our threshold? Well, our threshold is just 1 minus capital T1. So that's our t0. And so logistic regression can be done with multiple classes. We can do everything including betas for each class. So each class will have its own beta. We can let all the betas go to infinity, in which case we'll get a support vector machine. And so even now with multiple classes, everything holds pretty much the same way we've seen before. Okay. Now notice, however, that if beta is very large, then e to the beta is practically 1, or e to the beta w dot x is practically 0. So this means that we have p sub k of x is equal to 0, or p sub k of x is 1 over kappa, where kappa is the number of times that e to the beta sub k w sub k dot x is approximately 1. So notice that one difference is, as we get an arbitrarily large number of classes, rather than getting practically 0 or practically 1, we get practically 0 or practically 1 over kappa as our predictions. This is not a big deal as long as the number of classes is relatively small. But of course, if the number of classes goes to infinity, then the 1 over k goes to 0. So the point here is that even though we can extend to multiple classes and get support vector machines for arbitrarily large numbers of classes, in reality, as the number of classes becomes arbitrarily large, the ability to predict whether or not something is in a given class becomes arbitrarily difficult. So, something to keep in mind. Probably don't want problems with too many classes. So in summary, support vector machines are extremely useful. You just need linearly separable somewhere. And the kernel trick then is a really good trick. And there are natural extensions to multiple classes, which we just saw. However, choosing the right kernel is crucial, and it's a pre-processing step. Therefore, it's not only crucial, it's also a source of bias and misclassification. And the real world is complex, which is rarely separable. That's why we're going to look at some more tools, in particular neural networks, which don't need the concept of separability in order to do their type of classification.